All right. So last week we talked, why is it zoomed in this weird way? Okay. So last week we talked about reinforcement learning, we talked about the intuition and history, the Q learning introduction, and we talked about how we take actions, and then we finally formalized this and showed you the full Q learning algorithm. So if you remember, this Q learning idea was all about taking the world and trying to compress it down into this function called the Q function, which encodes how good it is to do something in a state. So how good it is to do some action in some state, right? So if you remember this, what was the Q function's like parameters? What were the parameters for the Q function? There was two of them. Yeah?
State and action.
Exactly, right? It was the state and the action. So the Q function takes in the state S and an action A, and what does it output? What's the output space, we should say? Yeah? The reward, right? It's not actually the reward. It's something that's related to the reward. It's not just what the reward you're expecting to get at that state, but it's some kind of metric about the future. Does anyone remember what the distinction was, or why it's not exactly the reward, but it's something a bit bigger, we should say? Did someone say return? Yeah, so it's return. So what's the difference between return and reward? You or anybody else? All right, so if we remember, we can go over this. This is, yeah, sure.
I think that reward is what you get in that state, or in that step, and return is the expected value over all of the rewards.
Exactly. So the reward, well, that is true, but there's one extra thing you have to add to that to make it fully correct, which is that the reward is what you expect to get this time step by doing something. So for example, like the reward you get this time step for eating a piece of chocolate is the reward exactly for that piece of chocolate, and that's it. The return is a discounted future sum of reward. So it's basically saying, like, in expectation, if I eat the piece of chocolate now, what is the value for me long term for eating the chocolate? And that's called the return. So let's just do a quiz. Do you think that the return for eating a piece of chocolate will be higher than the reward or less? So if I today eat, maybe not a piece of chocolate, if I eat a pound of chocolate right now while I'm giving this lecture, that'll be pretty good right now for me, but then probably like 15 minutes from now would not be that good. So what does that mean about the relative value between the reward and the return? What do we think? Yeah? Well, it won't be exactly less because technically the reward is part of the return, but it won't be that much more, right? Because you could imagine if you have negative values in the future, it could become less, so maybe you are right, it is less, but it all depends on the discount factor gamma. All right, so what is the discount factor gamma? What is that? It's that weird Greek letter thing that looks kind of like a Y, this thing here. What does that represent? Yeah?
Over a given time, like your set like rewards will continue to decrease over time.
Right, so it's basically saying not the set of reward, but the amount that you value that reward over time is less for rewards in the future versus rewards right now. So today, $1 for me is worth $1. But tomorrow, $1 might be worth, $0.9. And so I would rather have $1 today than $1 tomorrow, right? So that was the whole idea. This gamma thing is a number between 0 and 1. It tells you how much you value the future. Okay, so the way we learned this is we iterated this thing called the Bellman equation, which we derived last week, which was this really simple idea, once you wrap your head around it, that the Q function of one state today is related to the Q functions of all the states that are nearby me, right? And we saw that the Q value of the state that I'm in right now and the action that I'm going to take is some function of the state that I end up in after I take that action. So for example, if right now I decide to eat some chocolate, that is the action that I'm taking in this state, and the state that I end up in is the state of being full, right? That state itself has a negative future value, right? It's like, oh, I'm going to be uncomfortable, all these other things. So technically, the Q function today of eating the chocolate should actually be less than what I thought it was. So you can do this update where you periodically update the Q functions to get closer and closer to this true value where everything resembles the things around it plus or minus the actual reward that you got by transitioning from one state to the other. So it's kind of interesting, and this is really the most important equation, and we're still going to be talking about this exact same equation today, but we're just going to be doing it in machine learning land. So last week we talked about a policy which looked kind of like this, very, very similar to this. This is the Q table. So this is the table of all Q values. So it's for every state and for every action, what is the value of that state and action? So who wants to remind me, how do we take an action? So we have this Q value. Let's say I tell you that this is correct. This is the correct Q table. How do you actually take an action? Yeah, the policies. How do you define your policy? How do you get the policy from this table, basically? So I guess the question is, let's say you're in some state, one of these rows. Which of the columns do you take? Which of the columns' actions do you take? Yeah. You take the one with the highest value. Why? Why would you take the one with the highest value? Exactly. It's the one that has the highest future value. So maybe for me, eating some chocolate right now will have a really high current value, but a negative future value. But then something like drinking some water will have a medium reward now and a high reward later as well. So maybe it's better for me to actually drink the water instead of eating the chocolate. Right? So we factor in long-term consequences of our actions into the current world, which changes how we should value different actions that we take today. Okay, so I ended last week talking about how this table has a fundamental flaw if we're trying to apply this for real life or for any robotics task, chess game, almost anything we're going to apply AI for. We need this table to actually perform this AI search and do Q-learning. And what's the problem with that? Stochastic, so that is one big thing, but technically the Q-learning does factor in the stochasticity because of this expectation here. So in the Q function here, you're taking an estimate of the optimal future value, and I did have the expected value here, yeah, where you take the expected value. So that is already captured in the Q table, although it does make it more difficult to factor in static values for the Q. That's true. That's not the thing I was going for, although that is correct. Is there another maybe more obvious thing that would be wrong with the... So the action space, let's just say that I could write down all the actions. Let's say that it's not that the actions change necessarily, it's just that I somehow know every single action you could possibly take, and I can write those down. I can say that this is an action, this is an action, this is an action. I can tell you if something you do is a valid action. So you're close. That's very, very, very close to it, but it's not. So I'll give you more specific examples. If we wanted to do chess, we wanted to play chess with Q-learning, we would need one row for every possible state in the chess game, right? And I showed you last time that the number of games in chess that there are is, hold on, I had the number. It was a massive number. Where is it? I think it's here. Yes, so for chess, there was 7.7 times 10 to the 45 different states in a chess game. So that is more than the number of atoms in the universe. So we cannot store this table where we have one row for every state because we would not have a computer big enough to be able to store it, right? So it's just physically impossible to use Q-learning with chess unless we did a lot of things to simplify it significantly. Okay, so that's one issue, is that if you have way too many states, you can't actually do this. But in real life, this is maybe something that you were alluding to. In real life, do we have a number of states? Can you even enumerate all the possible states that there are in real life? No, because real life is this continuous thing that there doesn't exist a set of all states that it could exist, because anything you have, there's infinite variations, and so there's actually an infinite state space in real life. So even outside of things like chess, there could be domains where there's literally infinite states, where obviously that's not going to work either to store in a table. And then another thing that you mentioned is actions. I, right now, am not limited to what actions I can take. There is an infinite number of actions that I can take, right? I can arbitrarily constrain it to saying it's either chocolate or drink the water, but realistically, I can do one of an infinite number of things right now, right? So even that means that this table that we're trying to generate has infinite rows and infinite columns, and there's just no way we're going to do anything productive. So the idea here is that we want to use neural networks to approximate this Q table. So instead of having infinite rows and infinite columns in our table, we instead just have a neural network that you give it the row number and the column number, and it'll spit out the value at that place. Now, it's obviously going to be an approximation because the table is not infinite resolution, but it'll be pretty close. We've seen that neural networks are really good at doing a lot of stuff like image classification and unsupervised learning and language modeling and all these really cool things. So it's not unreasonable to think that it can do this too. And it turns out they can, and it turns out that this is actually some of the technology behind things like ChatGPT and how they actually work. Okay, so in RL domains where there's too many states, we can use a neural network that approximates the value function, V of S, and the state action pair value, Q of SA. Okay? And it might be really interesting, you might be confused about how you can do that, But it turns out that that Bellman equation that we looked at earlier can actually just be directly translated into machine learning speak to be used with these neural networks. Okay, so here's the most naive way to do it. And this way requires you to have a discrete action space, all right? So what that means is you need to have a number of actions that you can take where that number is some integer value, right? So it's not that, we're like one step closer, but we're not exactly fully there yet. So what you do here, oh no. Uh-oh. Okay, cool. So you have this neural network where you feed in the state, and it has one output for every action you can take. So this would work for something where there's an infinite number of states, but maybe 5 or 6 actions that you can take. And you can think a lot of video games are like that, where there's an infinite number of states that the game can be in, but there's really only 6 things you can do, like move forward, move back, move left, move right, or jump or something, right? So there's a finite number of things you can do, and that like really, really small number of things you can do, and there's an infinite number of states. So if you do that, you can just have a neural network where you feed in the state, and it outputs for every one of the actions what is the Q value. So this neuron would output the Q value of ST, the state in time step t, and the action 0. This one would take the Q value of state, the same state, action 1. This one would take the Q value and take action 2. And it would output 3 numbers, right? So this is perfectly reasonable for a neural network to do. We can just have it output 3 numbers. So now, with this neural network, how do we create a policy? How can I say, if I give you this neural network that works, what do you do to act optimally in this environment?
Get the artifacts from the last layer.
Exactly. So you take the neural network, and you take the argmax of the last layer, and that'll tell you the index of the highest action that you can take, or the action that results in the highest Q value, and that's the correct action to take at this state. So this is exactly just a mapping of the Q table. It's basically just a Q table, but we're representing it as this function, this neural network. That's a really complicated function that we won't get into how it actually works. It's just some function of the input that you can learn. All right? So is everyone convinced that if I could give you a function like this, it would be pretty much the same as having a Q table, but it would also work for whatever state you give it? And so even if you train it on 2 states that are relatively simple, and you don't ever train it on some state in between them, it actually turns out that it'll probably approximate pretty well what the Q value of that state in between them is. So this is actually even better than a Q table, because for a Q table to be filled out, you would need to visit every single state in your entire environment to be able to fill that column in. But this way, you can kind of fill things in by interpolating between 2 things that you've already seen. So if you've seen something like you've seen a black cat and you've seen a white dog, you can probably guess what a white cat would be like just by like mixing the 2 values for the white cat and the black dog, right? All right, I messed that up, but you get the point. So learning this function actually helps you with learning the Q values. Okay, so there's a video here I think I showed you last time, but this is DQN playing Atari Breakout. So DQN is this function, is this way that you can actually learn these functions just by optimizing this Q Bellman equation. And yeah, so how do we actually train this network? So we already know the target, so I know what to optimize the Q values to be, because we saw that already. The Q values is just some function of the future Q values in the state. So what you can do, and please forgive the math notation here, it's much easier than you think, it's that we take the label y, so remember we always denote labels in machine learning as y, and we say that it's the expected value of some state drawn from some state distribution of the reward that you got from transitioning into that state plus the discounted value of the future state. Now there's one big difference here, and it's this theta I minus 1, and I'll talk about that in a second, but for now this is exactly the same thing that we've seen before. This is just saying this is the expected value of some future state given that you're in a state and you take action A of the reward plus the discounted future value. Okay, so I want you all to squint at this for a bit and just see that this is basically saying that the correct Q value is just equal to the expected value of the reward you get right now, the immediate reward, plus the discounted future reward you're going to get from where you ended up after taking this step right now. So I'm going to quickly flash back to the Q learning function that we looked at, and I want you to see that this is exactly the same thing. So we have some old estimate, Q of STAT, and we have some estimate of optimal future value, which is R plus gamma max A of Q of ST plus 1A. And so all we do is we take this thing here between here and here, is all the actual Q target, as they call it, and we're just finding what's the difference from the target, and we're going to adjust our course so we can actually hit that target. So we're saying, here's the target, here's where we are, we're going to take the difference between that to figure out how off we are, and then we're going to move in the direction to correct for that error. All right? So I mean, it's pretty much a one-to-one mapping here, which is why this was such an easy method to come up with after the table method worked really well. And so DQN, you just optimize this, and the way you optimize it is by writing this loss function, which is saying the loss function is the correct Q target minus the Q value that I'm estimating right now. And you square that because you want to get mean squared error. So this is literally just a classification problem, just like we've seen many times before, where you have the thing you want minus the thing that you have, and you take the difference, and that's how wrong your model is, and then you want to minimize that loss using gradient descent or one of these other tools that we've seen. Okay, so we've covered a lot, so I want to pause now just for any questions at all, because this is today's equivalent of the most difficult thing that you need to understand, is that just like these two equations here, how do these do the same thing as those Q tables? All right, and then after this, we're pretty much done, and we can actually go and program the DQN. But yeah, so just I want to make sure everyone understands this, so we'll pause. Yeah?
Can you elaborate on why do we need S hats to be drawn from like all states?
So S prime here is not drawn from all states. It's drawn from the future state distribution given that you're at state S and take action A. So it's basically saying drawing from they call it the transition function. I don't know why it's like epsilon here. Probably should be something like T, like it's a transition function. So it's saying, given the state that I'm in right now and I take this action, what is the most probable state I end up in? So if I'm eating chocolate and right now, the most probable state I end up in is one of being full and uncomfortable, but there is a chance that I end up being super energetic and not, right? So it's some expected value of all these different worlds that I could end up in after taking the action. All right, so I want you to convince yourself that these equations make sense, and if you struggle with convincing yourself, ask me and I'll try to help you convince yourself that this makes sense. So this is the same thing. To answer your question again, this is the same thing as saying we're drawing S and A from the transition function rho here, which is the same kind of thing here. All right. Speak now or forever hold your peace. Yeah.
Can you explain the loss function?
Yeah, the loss function. So if everyone remembers, in machine learning, you want this thing called the loss function, which tells you how bad your model is, and then you minimize that just using multivariate calculus. So this loss function is just defined as, it's the expected value of drawing a state and action pair from your transition function, and you take the estimated Q value, which is this big ugly thing, and you subtract the current Q value. And you're saying, I want my current Q value to be as close to the estimated Q value as possible, and then you square that, and then that is the loss. Yeah?
This is effective for any network architecture?
This is assuming this kind of network architecture. It doesn't matter if it's a convolutional neural network or a language model or a transformer model. It really doesn't matter. As long as it takes in the state and outputs the Qs, this will work. Yeah, so often people actually, in this game for the Atari breakout, which I showed you at the end of last time, the actual policy took pixel data. So the neural network, the state was literally just pixels, where you would just play the game just like humans would play it by watching the screen, instead of giving it some lower dimensional state representation, as they say. Okay, everyone clear on this? This all make sense? Okay, awesome. All right, so I guess there is a Google Colab today, so I'm going to do this, and then I will share the Google Colab with everybody, where you get to actually play with deep Q networks and train them yourself. Here we go. I hope it still works. Yes, okay. All right, is everyone on the Discord? Should I just post it on the Discord? Would that be good? Okay. Okay, so open up that Google Colab, make a local clone of that, and then I will walk you through what that code is actually doing. All right, everybody have that up? Okay. So I don't know if everyone's heard of Gymnasium before. Has anyone heard of Gymnasium? Hands up. Okay, who here has heard of OpenAI? Yeah? So before OpenAI was making things like ChatGPT, they were making this reinforcement learning library called Gymnasium, which is a really simple environment that sets up basically a two-dimensional world for most of these tasks where there's an agent acting in the environment. So this is a task called cart pull, which is one of the most infamous tasks for reinforcement learning. It was actually the task that they solved here at UMass in the 80s or so with reinforcement learning, with the tabular version of reinforcement learning. And the way this game works, pretty simple, is that you have some kind of pole in your hand or in a cart, and the goal is to balance the pole from falling over. And it has like correct physics and everything. So you can imagine you could actually try this and figure out that it's pretty hard to do, where you have like some long pole and your goal is to balance it so it doesn't fall over. And the reward of the agent is the length of time that it takes for the pole to fall over. So the longer that you live without dropping the pole below the horizontal is the more reward you get. All right, everyone clear about what the task is? Now, the action space here is pretty simple. The action space is literally just, do you turn left or do you go right at this state? Do I go left or do I go right? And so your goal is to balance the pole by moving left and right sequentially and keeping the pole as upright as possible. All right.
When you say solve, what do you mean by solve? Like, it just go on for forever?
It would, the optimal policy could play this game forever. Yeah, so you could literally balance the pole for forever. Like actually, like as long as your simulation wants to run, you can balance the pole, which is probably pretty hard for humans to do. So we already beat humans at something. But yeah, so if everyone's clear on the task, now it looks like it's like the pole is actually stuck there, but believe me, the pole can do a full 360 here. So this is like a pivot here, but it's not actually, there's no friction between the pole and the cart. So the pole could literally just fall right over. And if you try to play it yourself, it's actually a very hard game to play. So it'll be good if we can get our agents to play it now. Okay, so first thing we'll do is just install all the packages. So make sure you run this. This will install like the Gymnasium package from OpenAI. It will install this Pi virtual display that you need to be able to play a video in Google Colab. And yeah, so this right here, pretty simple code. This is just like importing all the libraries that you need. Now, okay, so this is a pretty interesting also piece of code. This is called the replay buffer, and this is very important for how Q-learning needs to work. Oh, is your hand up? Oh, okay. So in Q-learning, you don't just want to train on the current situation. You also want to train on your memory of the past. So if you remember, like today, oh, I ate some chocolate, I feel really good, but 2 years ago, I ate chocolate and it made me like really, really sick. I probably should remember that 2 years ago I did that, and so I should probably update my value of chocolate today, given that 2 years ago I got really sick eating the chocolate. So this whole idea of the replay buffer is just to say, I should remember the things that I was trained on in the past, because I might have forgotten by now. So you want to, every once in a while, bring some memories in and use those to train yourself in the present so that you don't make the same mistakes as you've already like stopped making. So maybe you learned something in high school, and then you come to college, and by the time you're done with college, you forgot the stuff you learned in high school. You probably wouldn't want that, and so, I mean, it happens to all of us, but you probably wouldn't want that severely hindering your agent's performance here. So it's pretty simple. It's just a queue for everyone here that's a computer scientist. It's just a simple queue. Okay, so we already saw the DQN algorithm, so I won't go into too much depth about it here, but you're basically just implementing that where you have the neural network. So you should all be familiar with what a neural network looks like and does. If not, no problem at all. I'll talk you through this really simple code. So we have a neural network that inherits from the PyTorch module library, which basically means that PyTorch creates this library called a module, and you inherit from it with object-oriented programming to be able to build yourself a neural network class that follows the same functions that the neural network module class should have. So this gives you a lot of functionality. So the first thing we do is we initialize the super. So basically we initialize the parent class, which means we initialize the neural network.module class. And then we create 3 layers. The first layer goes from the observation space size to some number, 128 I chose. And then the layer number 2 goes from 128 nodes to another 128 nodes. And then the final layer goes from 128 nodes to the number of actions. All right, so who wants to remind me, why is the input space the number of observations and the output space the number of actions? Why is that? think back to the image that I showed you. So the question was, why is the first layer take in n observations as the input and n actions as the output? Why is it that order? Why is it not n observations, n actions as input, and 1 as output or something? So remember the neural network. What was the input to the neural network in the image, and what were the outputs of the neural network in the image? Exactly. So the observations is the state of the world, the physics and the place of the pole and the place of the cart and the angle and the angular velocity and all these things. And then the number of actions is just saying everything that you can do, because you want to store one Q value for everything that you can do, right? So for everything, every state, there is going to be n outputs, where n is the number of actions. And each one of those things is going to be the Q value of taking that action in that state, right? So for example, if the pole is just about to fall over, and if you turn left, you'll actually save it. But if you turn right, you won't save it. The pole will keep falling. The Q value, the first Q value, the one for going left, will be higher than the Q value for the one for going right. Because if you go right, it's going to end in the pole collapsing. But if you go left, it will end in the pole not collapsing, and you get to survive for longer. So in the state of pole nearly fallen over, the Q value, the first node output, should be higher than the second node output, if we decide that left is first and right is second. Okay? And we also just do ReLU in between them so that we don't get too many exploding gradients, and makes it easier for nonlinearities. All right, so this is maybe the most daunting part of the code, but it should be relatively self-explanatory once you saw the equation that I showed you, which is that we basically, oh wait, this actually is not the training code yet. So we create a policy network, DQN, we create a target network, DQN. I won't talk too much about the target network, but effectively we're doing the same equation that I showed you before. We have a way to select actions, and we should all know how the select action works. We should be able to take every single one of the policies, right? And then we take the max of it, and then I guess it'll return the largest column value of each row, right? So this is saying for every state, we're going to return the largest column value in each state, which is basically going to be the actual value of each action. So it's going to return what action we want to take. So given the state, we're going to take the action that has the highest Q value. So it's the action that results in the highest value in the output of the neural network. All right, so here's the training loop. We're sampling a bunch of data. We're going to get the state action values from the policy network. And then all we do is we say that the expected state action values is equal to the next state values times gamma plus the reward. Remember, we saw that. This is y underscore I. This is the correct label. And then we just say that the loss is the mean squared error. This is what criterion here is, of state action values and then the expected state action values. So we're saying that we want the state action values to be as close as possible to the expected state action values. And then we just take a gradient step, and then we clip the gradients so we don't have exploding gradients, and we optimize. All right? And then this is the actual training loop where you actually sample from the policy, you sample from the replay buffer, and you do Q-learning. And so when I ran this, this is the result of the duration versus the episode. So episode is basically how many times you trained on the cart pool environment. So how many times did you get to try playing the game? And the duration is how long you lived until the pole fell below horizontal. And so you can see, once you get to 500, that's the maximum score, we got there within about 350 episodes. So 350 times playing the game, we got an agent to go from not being able to play at all, getting close to 0 time, to actually being able to balance the pole pretty much indefinitely. So you can actually run this yourself now and try to mess around with the different parameters like gamma and the training step and all these other things, and you'd probably get different results. But you hope that it goes up and to the right. If it goes up and to the right, you are solid and you are reinforcement learning. So that is pretty much it. And I also wrote some code here in case you're interested for visualizing the policy. So if you want to see what it actually looks like, you can watch it. So here's the policy that we created. So it's doing pretty well. I mean, it's balancing the pole pretty much optimally, right? So this code is general purpose, so you can change any environment to any one of the gym environments here. So you can make this, instead of cartpole v1, there's a bunch of different gym environments you can use, and this code would just directly work if you just change that string. So I encourage you to mess around with the other gym environments. Yeah, there's a lot of them, so they're very cool. Okay, so just a quick poll now for what we want to do. It's 7:35 right now, so would you all rather spend the last 25 minutes going through the code, making sure everyone's had a chance to play with it, and that's it? Or would you rather play with the code later on your own time or while I'm talking, and then have me talk about policy gradients, which is a way to deal with infinite action space as well? It's going to be the most math-heavy thing that we've seen probably so far in the club so far. All right, vote now. So who wants to just do the Google Colab and just work on that? It's okay. It pretty much doesn't matter. All right, who wants to see policy gradient stuff happen? Okay. For the people that wanted to do the Colab but didn't want to put their hand up so that they wouldn't be the only people, feel free to just keep working on the Colab and ignore what I say. Okay. But for everyone else, feel free to listen as well. Okay. So this is going to be pretty math heavy. I apologize in advance, but you all signed up for this, so. All right, so far, we've dealt with this issue of infinite state space, but we haven't dealt with the issue of infinite action space, have we? Right? Because the only way that we could deal with infinite action space is if the output of the neural network was infinite number of nodes. And even worse than an infinitely big table is an infinitely big neural network. So that's not going to help us too much. So how can we actually deal with the fact that the state space is continuous and the action space is continuous in most domains in the real world? How can we deal with this fact? So the hint here, and I actually want someone to try to think about it, the hint here is that when we went from a table to a function, we took the thing that was continuous and made it the input to the neural network. So now, what can we do? What can we do to deal with both of them? Yeah?
Make the output continuous, but instead of like one node, maybe have a few more nodes that have some like full value in it. That sounds like rotation change or speed change.
Yeah, that's a very good point. So you could have multiple nodes that instead tell you like a continuous value for what you should change. So basically, you have the input space being the state, and the output space is still the action, but it's not saying for every action it's the Q value, it's just directly the action. But didn't we already see that before? What did we call a model that takes a state and then just directly gives you the action? What did we call that? There's a word. It starts with a P, and it's denoted by the Greek letter. Yeah?
Policy.
A policy. So the idea that you just suggested is called policy gradient, where instead of learning a Q function and then converting that Q function into a policy by taking the argmax, you can just directly learn a policy. Wouldn't that be so much easier, right? So we can directly learn a policy from online gameplay. Because technically, us as humans, I mean, this might be bad to say, so if it's recorded, please forgive me. But us humans are basically just policies, right? We're just, you take in a state, and then we output some kind of action, and we're not doing, I mean, some people would argue that we're doing some kind of Q function where you model the value of your actions or whatever. But for the sake of this example, we are just policies, right? We act, and then we learn about our actions, and then we take better actions in the future. It's not like we're learning a Q function and then only act by taking the argmax of all the things we can do, right? So, yeah, thank you. So the policy gradient, effectively, is that we have some policy, pi theta, and we're going to normally build this after creating a Q function. This is with dqn. But why can't we just directly learn the policy? And this is all these algorithms called the policy gradient algorithms. You might see them as PGA policy gradient. Okay. So this is the really simple intuition for how policy gradients work. It's basically just the idea that you want to push up the probabilities of actions that led to a high return and drop down the probabilities of actions that led to a lower return. So as I said before, if I remembered 2 years ago that eating chocolate made me really sick, I just want to decrease the probability that I would output the eat chocolate action again, right? So if maybe this happened to some of you, is that you were eating at a restaurant, maybe some seafood, and you got really sick after eating at the restaurant, and you never will eat that seafood ever again. You're just completely averse to it now. So the probability of you taking action, eat the seafood when you're at the same restaurant again, will be close to zero. And your brain did that update in like one day, one really bad day, and you decided that you're never going to do that again. So this is the idea, and this kind of makes sense for how humans learn, is that if I did something that led to a really high reward, I'm more likely to repeat that series of actions again. Right? So this is a pretty simple dopaminergic system. And now some math. So this is called the J function, also known as, you can think of it as the return function. And all that it maps is that it's the expected value for every trajectory that the policy outputs. Okay, so you can imagine this is basically every life that the policy would ever live, every life that I would ever live by following some policy, and it's just the return of that trajectory. So this is probably the simplest one that we've seen so far. This is just saying, given a policy, what is the expected return I expect to get by following that policy? All right, so I'm gonna tell you two policies, and you have to predict whether the J of theta 1 will be higher than J of theta 2 or the other way around. So theta 1, pi theta 1, is going to be the policy such that every time I walk into a door, I instantly leave the door again. So I walk into a room and I instantly turn around and leave. That's just my policy, no matter what. So if I'm about to enter class, I turn around and leave. Unfortunately, I just can't do it. And then policy number 2 would be whenever I enter a door, I continue walking through the door, and I do whatever I'm meant to do on the other side of the door. So these are two policies that are perfectly reasonable, maybe not perfectly reasonable. Which one would lead to a higher return, do you think, in my life? Or a higher expected return? You can't know for sure. You can just predict based on what you know which one would lead to a higher return. So what would be a better policy to follow? The policy of always turn around before you enter a room. So you walk in and then turn around and leave, and you can't actually go in the room. Or the other one is just to walk in the room like normal. This is probably the worst example I could have come up with, but it's the first thing that came to my mind. Yeah, so it's pretty much clear that walking in and doing the thing is probably going to lead to the highest return. Like, if every time I tried to go to the dining hall to get some food, I turned around and left, I would not last that long, to be honest, right? So it seems like the one that has a higher expected return would be the one where I go through doors normally, right? So that's why we go through doors normally, everyone. You learned something new psychologically. So now the question is, if we have this J function, this tells us how good a policy is, we can just take the derivative of the policy's goodness and take steps to improve its goodness, right? Isn't it that easy? So if we can just find this derivative, so if you know this derivative sign, so we're taking the gradient with respect to theta of the value of policy pi theta, then we can just optimize the parameters theta by saying that the next parameters are equal to the old parameters plus some learning rate of the derivative of the policy, of the value, right? All right, so there has to be a gotcha here. This can't just be that easy. What's the gotcha? Does anyone have an idea?
How are you going to know what function to take the derivative?
Okay, that's a good point. So we don't actually have an explicit form for J of theta because it's some expected value over every single possible lifetime, which we can never simulate. So we can actually guess what J of theta is by just running a simulation over and over again. It's called a Monte Carlo simulation. So that is a problem, right? So that is one of the big problems, that we don't know what J of theta is. Now, because we don't know what J of theta is, how are we supposed to take a gradient with respect to theta of this function that we have no idea what it is? So what you're about to see, please forgive me, okay? But this is how you do it. It's not that bad once you actually look at it, but it did take a few tries when I was first learning this to really understand how this math works. I will go through it really quickly, and if you have any questions, please come talk to me after. But it's not that important that you get this fully, but I'll talk you through step by step. Okay, first thing is this. We've all seen this. This is saying that the derivative with respect to theta of our value, or of our J function, which is the expected return, is just equal to the gradient of the expected value if you draw the trajectory from your policy by living the life of that policy, and the return of that trajectory. So this is basically saying for every lifetime that the policy has, what is the return of that lifetime, right? This is just equal to the integral over every single trajectory of the probability of the trajectory under the theta, so the probability of the trajectory given that your parameters are theta times the reward, right? This is just a weighted sum of every single possible trajectory you could have multiplied by the reward of that trajectory. And therefore, you can take the gradient inside, and you can just say that this is just equal to the gradient of the probability of the trajectory given theta to multiply by the reward. And now this is this really important thing called the log derivative trick, and it's basically saying that the derivative of this is equal to this. Okay, so basically saying that the probability of some trajectory given theta multiplied by the reward of the trajectory, the derivative of that is just equal to the probability of the trajectory given theta multiplied by the derivative of the log probability of the trajectory given theta reward. Which is kind of interesting because then you can just reverse the integral, right? You can just return it into the integral form, and you can say that now this is just the expected value over every trajectory given in every trajectory that the policy generates, multiplied by the gradient of the log probability of the trajectory given theta multiplied by the return of the trajectory. So what this means is that now you only need to evaluate the log probabilities of these things. Now, who remembers from maybe if you've taken a math class, why are log probabilities easier to work with than just regular probabilities? So so actually almost everyone could be able to answer this question if you've taken, I think high school math, is that when you take logs, if you multiply A and B, what is the equivalent of doing that in log world?
Adding.
You add them, right? And so in your computer, you might know that adding is way easier than multiplying. Because adding, you can just take the bits and just align them and do it really, really quickly. But multiplying, you need to do this like order n operation. If you want to learn more about that, that's actually in 311. They talk about the complexity of multiplication. But essentially, you should know that multiplication is much more expensive than adding. Storing log probabilities is much easier. And so you can write out this equation now, which is just saying that essentially the derivative of your j function is equal to the expected value of some trajectory sampled from your policy of the sum for every time step from 0 to the end of your lifetime of the log probability of taking action A given state t multiplied by the return. So what this means, this is basically saying what is the probability that I take the next action given this state, and you take that sum over my entire life, that actually gives you the exact same thing as the probability of the whole trajectory given theta. And so you can take this equation, and this gives you the grad log problem, right? And this can be estimated. So this is an expected value. You can't just enumerate an expected value. So you can just estimate it by taking a sum over every single one of the demonstrations in your data set. So you take a trajectory from your data set, you divide by the length of the data set, and then you take the time step. So this is the same thing. This is the probability that you take an action in your lifetime and the gradient of that. So now, what is the issue anymore? So your problem before that we had a j function that we couldn't differentiate, is the j function here anymore? Do we have a j function anymore? No. So what are we differentiating now? What is the thing that we actually have to take a gradient with respect to? What is the function that we're differentiating? Is it something that we have an analytical form for or not? So I'll just pause on that for a second. So remember, we didn't like this because this was the gradient given theta of the expected value of this, just the gradient given theta of this function. And we didn't know what this function was because it's some expected value that we can't actually calculate. We don't have an equation for the expected value of a trajectory. Right? So we couldn't take this gradient because this here is unknown. We don't have a mathematical equation for it. But now, all that we're taking a gradient of is this stuff here, right? And do we have an equation for that? For log pi theta at given s? Do we have a written down equation of that? So, okay, let's step back for a second. So what is pi theta? Who wants to remind me? What is pi theta? It's easy to get lost in the weeds here because there is a lot of weeds, but anyone remember what pi theta was? Pi sub theta? It starts with a P. It's the thing that we're creating with this system. Yeah? Exactly, it's the policy. And what is the policy in this setting? Like, what does it look like? So in the DQN network, the policy was an argmax of this Q network, neural network, but then what you suggested was that we can just directly have the policy being a neural network that maps from the state to the action, right? So the policy here is just a neural network. This pi theta is just a neural network. And it's a neural network, not only just any neural network, it's a neural network that we have on our computer. Right? It's a neural network that I have on my computer because I created it. So I can very easily take the gradient of the log of that pi probability, right? It's very easy to do because I just have the neural network. We take gradients of neural networks all the time. That's what this entire club is about, basically. And so you can do this gradient here very, very easily by just saying, I'm going to take my policy, which I have. I can take the log of that policy. That's fine to do, too. We know what the derivative of the log is. And I can just take the derivative of the log probability of my policy, the log probability of taking some action in some state. So with doing all this math, all that we do, and this really, really complicated math that helps you do this really simple thing, which is saying that all I need to do is to increase my value of this policy, to increase how good my policy is, I want to just increase the value of the policy probabilities for the ones that have high reward and decrease it for the ones that have low reward. Right? So we want to increase this. Remember, the gradient, we want to increase this for rewards that are high, and we want to decrease this for rewards that are low, because we want this thing to be as high as possible here. That's just how the gradients work. So if this doesn't make sense, absolutely no problem. It didn't make sense to me the first or third or fourth or fifth time that I looked at it. The sixth time, it made a bit more sense, and then after like the 12th or 13th time, it finally like clicks. So don't worry at all if it doesn't make sense. But yeah, so really intuitively, you have to think that we're just taking a gradient of how good a policy is, and the gradient of how good a policy is just the sum of all the things that you've done. The probability of the things that you've done that are good should be higher than the probability of the things that you've done that are bad. Right? And you can just directly do that. And the result of this is that you can actually have Pong playing AI, which is, it's kind of funny that you put all this time and math into deriving this and then you play Pong with it, but that's how the researchers are. Okay, let's hope. So my YouTube was broken last time, and you'd think that a computer science senior would be able to figure out why their YouTube is broken, but I think that's too, okay. I think it actually might work. Oh my God, I think it works. So note to self, if you ever want to fix your computer, do a presentation in front of people and say that it's broken, and then it'll start working again. Okay. So this here is, I believe, 2 Pong agents that are being trained with AI, that are being trained or trained with the policy gradient algorithm that we just saw. So why does it make sense here to use the policy gradient algorithm? Well, you can imagine that in Pong, the action space, you could have it as discrete, or you could have it as continuous. If it was discrete, it would just be, do I go left or right, or I'm sorry, up or down in this case. If it's continuous, it would be, do I want to go left or right, or by how much? So maybe I want to go up by more this time or less this time, right? So you can actually do that and get a continuous action space if you want. But there's no reason that the policy gradient has to work for continuous action space. You could get it to work with discrete action space, no problem as well. It would take a few modifications, but it could work. And there we go. So what you'll notice is that on the left, actually, this is not an AI. On the left is just a deterministic thing that just goes up and down. And on the right is the actual policy gradient algorithm. And the score is 9-1, so it seems like it is working, although it did just lose there. Yeah, so this here is completely in reach for every single one in this room. So if in the spring, when we start doing our projects, which I'll talk about probably now, actually, in the spring, when we talk about our projects, if you want to do something to do with reinforcement learning, I would highly recommend it. It's the most visual and most fun type of project to have, because you get to see things like this, and you get to pick your game, and you get to build something that works in the game. All right? So hopefully that's motivation enough to get this to work. Okay. So last but not least, I think we're done, actually. I don't think there's anything else in my presentation here. Oh, there is, actually. So the question is now, I just showed you DQN, which is the Q learning algorithm, and I showed you the policy gradient algorithm. And what is the real difference between them? Well, the pros of policy gradient is that we have a messy world. If the Q function is too complex to be learned, then DQN may fail, but policy gradient might still find a good policy. So we're learning, for Q learning, we're learning this much more complicated thing, and then we're using it to act, when maybe we can just directly move to the actions and it's easier. It's also usually converges faster. It also can allow you to have stochasticity, where you're capable of learning stochastic policies. So you can learn, sometimes take this action, sometimes take that action, which is what the guy that was sitting over there said at the beginning. And also there's continuous actions, which is that much easier to model continuous action space. When you have actions that are infinite, it's not only much easier, in fact, it's actually like the only way you can model, well, there's many ways, but DQN cannot model continuous action spaces, because then you'd have to somehow have a Q function that outputs, it has an infinite number of outputs. Although you can get it to work by making it take a state and action if you wanted to, but that's going to be talking about DDPG and some other algorithms that we don't want to get to. So data efficiency, it usually is much more data efficient for DQN, because you can just train this Q function at once, and then once you know how the world works, you can just use that to perform well in the world. It's usually much more stable as well, and it's easier to determine what states, like which state action pairs, result in good reward. So this is called the credit assignment problem. It allows you to actually say, okay, so I spent a lot of time in these states, and those resulted in really good reward. Whereas with the policy, you have no idea really what happened, because you're just living life and you're looking at returns over your lifetime. And yeah, so that was probably everything you're going to need to know about deep reinforcement learning to do really well in pretty much any project you want to build. But there are some small intricacies that if you wanted to get projects to work in every single domain, there's a lot of different algorithms that get it to work in different types of domains, like ones that have continuous action spaces, discrete action spaces, ones that have high state space, ones that are really weird, ones that can't differentiate through. So there's a lot of different ideas, and I would be very happy to lecture about any one of these three things, any one of these four things. But they're way too complicated and they're very intricate, and so I don't want to waste everyone's time by going into the detail on them. As long as you know policy gradient and you know DQN, you're going to be better than 99% of people understanding reinforcement learning if you fully understand just those two algorithms. So these are four of the really most important ones. There's asynchronous advantage actor critic, or A3C. There's deep deterministic policy gradient, DDPG, which is one of my favorites. There's policy optimizations like trust region policy optimization, proximal policy optimization. PPO is the most like state-of-the-art nowadays. It's what they use to train ChatGPT. They use PPO. So proximal policy optimization. Proximal means that you want the policy that you're creating to be proximal to the policy that you have right now. You're trying to optimize a policy given that you don't move too far away from the policy you have right now. So, and that's also what trust region policy optimization does, where you have a trust region saying that, oh, my policy is pi theta right now, and I don't want to ever get too far away from pi theta because I might be so weird that I lose a model of the world. So I guess an example just for context is that if I live at UMass my entire life and I learn a really good policy for UMass, I don't want to suddenly go and live in Boston, because the optimal policy for living at UMass is way different to the one in Boston. So if I go to Boston, I would definitely do horribly. And the way to actually transfer to going to Boston would be I slowly, incrementally get there. I don't want to just take a massive leap, or else I'll end up in a place where I just can't learn at all. Same thing for TRPO. And then finally, evolutionary strategies. This is a way that you can learn when you have a population of solutions and you want to utilize the information from all the populations. This works if they're not differentiable either. So that's also interesting. So you can have policies that you can't take gradients through. Okay, so that's everything. I'll be here to answer any questions, because I know that I went into the weeds, so there might be a lot of questions. But thank you all very much. So a few quick announcements from us. We have actually a lot of announcements. So first off, next semester we're doing projects. So if you're interested in doing a project, make sure you come to the first meeting next semester, and also are active on the Discord, because we are going to be sending out a form that will gauge your interest into what topics you want to do and whether you have a team or not that you want to work with. And we can either allocate you a team, or you can work by yourself, or anything else. So we're pretty much open to any type of projects. But the whole idea is that every week you'll come back here, you'll meet with us as lecturers, and you get to build your project incrementally. And so you get to work on pretty much whatever you want, and you'll have advice from someone that's probably built something similar in the past. So I think it's going to be a really invaluable resource. And then at the end of the semester, we're going to have a poster session where we'll have a big, we're going to invite a bunch of guests, and we're going to have food, and you get to present your work to professors and other people to help, build an image for yourself and all that stuff. And you can also put it on your website or LinkedIn or anything like that of all the projects that you built. So I really recommend trying hard last semester. We had some really cool stuff last semester, so I really hope that we can get some even cooler stuff this semester. It'll make you all look good, so that's great, and it'll be a good chance for the lecturers to practice, mentoring a project and stuff too. So that's the main thing. The second thing is that we are going to have new officer positions opening next semester, just like normal. We have a full cycle, so if you're interested in being an officer at the club, feel free to fill out a form. We'll probably send out a form sometime in between the two semesters. So if you're interested, start thinking now if you're interested in doing that. We'll also be having presidential elections, because I am graduating in one semester, so we're going to start doing that. We're still working out the details, but you will probably be voting in some kind of thing where we'll have people come and give like a 2-minute pitch about why they should run Mass AI, and then we'll do some kind of voting to help figure out who should be the next president. And what else is there? Oh yeah, so on November 7th, I believe, there is a panel discussion where we're going to have a bunch of professors from industry and from academia, so ones that have spent their whole life in academia and others that have been in industry and then transferred to academia, to talk about the differences between them. So if anyone's interested or has questions about whether they should continue on in like a grad school or all these things in AI or in computer science in general, or if they want to go on to the industry, then that's a really good resource. I think it'll be really, really interesting. And then there's one more thing that I'm missing. Also on the same, I feel like on the same day. Isn't there, oh, the networking night, right? So we're also planning on doing a networking night. Do we have a date for that yet, or is that not set?
Yeah, it's the 19th.
Okay, so we will have a networking night on the 19th of November, and that's going to be, I think, right before Thanksgiving, right? So right before Thanksgiving, we're going to have a big networking night where we're going to have food, and we're going to have a bunch of people invited at the CS building, and it's more of a social night, and we'll just like basically get to talk to people and chat, no lecture or anything like that. We'll give them more announcements closer to the date there.
One more thing.
Yeah.
The CFAR 10 competition, we're having one to train like a neural network to classify images, and that's going to be the Sunday after the upcoming hackathon.
Okay, so Sunday after Hack UMass, by the way, everything here we're going to relay again through messages, but it's better to say it in person. So the Sunday after Hack UMass, we're going to have a competition on image classification for the CIFAR 10 data set. So if you're interested in partaking in a machine learning competition, that's a really cool resource. It's like 3 hours long, right? We're going to do, so 3 hours, you get to build from scratch your model. You have to have everything written with code on Google Colab, and you train it. We're going to try to get a bunch of Colab credits to get you to be able to run all your models. And really excited to see who can get the record. And I think we'll have some kind of prize for the people that have the highest accuracy model. Yeah.
Will we like learn how to do that over there, or like are you expected to know how to do it before?
That's a good question. Would it benefit everybody if we did like 20 minutes of how to interface with CIFAR 10? I mean, you should. I mean, you're not going to be completely from scratch because you have been coming to the club meetings and stuff. So we do have the resources there, and there's also a lot of online resources that we can use. Yeah, Nathan?
The notebook that we were planning to distribute as like a blank notebook for people to write their stuff in essentially starts with interfacing with CIFAR 10, and also the like introductory slideshow talks about like what form this data takes and does a quick review of like if you have color images, what is some stuff you might want to do to deal with that.
I see.
Because that's like the big difference.
Okay, yeah, that sounds good. So I don't think it's fair if we do a lecturer team, but I think that would be fun to do as like a baseline. But obviously we're not in contention for the prize, just to see if we can beat the people in the club. That would be fun. So yeah, if you're interested, obviously you don't have to be a member of the club to partake in any of these events. So if you have friends that you think would be interested in coming to these things, that would be cool. So the goal is that you don't have to be coming to the lectures to partake and make the most. And actually, in fact, a lot of people that would make the most of it are people that don't come to the club as well, because there are a lot of people that are like seniors or juniors that came to the club the first 2 years, and then we teach the same stuff over and over again, so they have no need to come to the lectures anymore. But there's still expertise will be useful for the competition. All right, is there any other announcement that I'm missing?
Well, we have the workshops that we're doing during hackathons.
Yeah, so who here is partaking in Hack UMass this year? All right, I hope to see you all there. This is going to be a crazy year. So Hack UMass, for those of you that are freshmen, is this like hackathon that's overnight. It's when I first drank 8 Monster Energies in one night, the worst decision of my life. Maybe not the worst decision. We won some prize. We didn't win like the main prize. I think we won the funniest hack. I can actually tell you guys what we did. So when I was a freshman, we did Hack UMass. Our project was I was working with my roommate who is a computer engineer, and we built a project that attaches to your computer's webcam and can tell if you're wearing a mask or not in class. And if you wear your mask incorrectly, then a picture of the old chancellor would pop up from behind and he would like wag his finger at you. It was like a full robotics thing. It was crazy. Anyways, so we won the funniest hack. It was mostly a joke. Oh, and then also it put your picture on like an online hall of shame for people that have their masks wrong. It was a crazy time. Okay, anyways. So.
That's really good.
Yeah, it was pretty fun, and it was pretty with the times, because I was like 2021, so. But yeah, so if anyone's interested in Hack UMass, we're going to have some workshops there. I think, Nico, you're going to be giving one of the workshops, right?
Yeah, I want to do an introduction to the OpenAI developer platform.
Mm-hmm. Yeah, so if you're interested in learning how to query API tokens for the language models, OpenAI is super useful. There's a lot of things you can do. You can pretty much do any one of these tasks that we've done in this course by just querying the OpenAI API and asking like ChatGPT to do it for you. So that's a bitter lesson from all this stuff that we're learning. But yeah, so tune in to Nico's lessons. Do we know if there's anything else that's happening? Yeah?
We're doing a MNIST training workshop as well.
Okay, so actually, we're doing MNIST training on Hack UMass. So if you're interested in partaking in the SciFar 10 competition, I recommend you come to the MNIST training, because MNIST is just another image data set. It's black and white, but it is also going to learn a lot. Yeah, thanks. And then, did you have anything to add? No? Okay. All right, sorry. I held you guys a bit over, but feel free to come and chat afterwards. I had a great time giving the lecture. So next week, do we know what's happening next week? I should have pulled up the lecture thing. Do we know what's on the lectures for next week?
Imitation learning.
Imitation learning. Who's giving that? Is that Trung giving that?
Trung is giving that.
Okay, yeah. So next week, we're going to talk about imitation learning. Very similar to reinforcement learning. Super fun. And it's how you learn when you know what optimal behavior looks like, but you don't have a reward function. And the answer is you imitate it. Yeah. Okay, thank you. Thanks for coming.
Well, that's